All right, welcome to today's explainer, where we're going to take some pretty complex network topologies and translate them into a literal map of the Internet of Things, the IoT universe. If you've ever found yourself wondering how billions of smart devices manage to talk to each other without completely collapsing the global internet, well, you are in the right place. Today, we're breaking down the exact network architectures that make all this distributed computing possible. We'll be exploring the three core communication models: edge to cloud, fog to fog, and machine to machine. Here's our roadmap for today. First, we'll map out the IoT universe, then dive into the edge to cloud vertical flow, check out fog to fog horizontal coordination, drop down to machine peer-to-peer, and finally, wrap it all up with the ultimate recap. Let's get right into it. Section 1, Map of the IoT Universe, Establishing the Hierarchy of Devices. Before we can talk about how the data moves, we first really need to understand the three core layers where our devices actually live and operate. Think of the whole IoT setup like a giant three-tier pyramid. Down at the very bottom, we have the things, right? Your edge devices and sensors operating right on the fringe of the network. Then, sitting just above them in the middle layer, we've got the fog. This is made up of local gateways acting as intermediate aggregators. And finally, sitting all the way up at the top, you have your massive cloud data centers. How data moves vertically or horizontally across these three specific layers is literally what defines our communication topologies. Moving on to Section 2, Edge to Cloud, the vertical flow. These are the heavy lifters of the network. Let's take a look at our first communication model, which is all about sending data all the way up that pyramid. You'll often hear the term north-south traffic, and honestly, it perfectly describes this vertical journey. Your edge nodes, down at the bottom, collect raw data, maybe do a tiny bit of basic filtering, and then just push all the heavy computational lifting straight up to a centralized cloud server, like an AWS or Azure data center. Now, you might be wondering, why send data thousands of miles away in the first place? Well, it's for the math. The cloud provides massive mathematical heavy lifting. It gives us incredible centralized visibility, intense analytics processing, and practically endless long-term storage. But there is an inescapable trade-off here, and that's physics. Sending data across vast physical distances inherently creates higher latency. It just takes time for data to go all the way up and come all the way back down. To really put why that latency matters into perspective, picture an autonomous Tesla cruising down the highway at 70 miles an hour. That car is the edge node. It absolutely cannot afford the delay of asking a distant cloud server when to hit the brakes. Literally, waiting for the cloud would cause a crash. So what does it do? The system intelligently splits the workload. While it's driving, it relies 100% on local edge processing for those split-second, life-saving decisions to avoid crashes. But it doesn't ignore the cloud completely. At the end of the day, when the car is safely parked in your garage, it flips to the edge-to-cloud model to bulk upload summarized telemetry, stuff like battery health or mapping updates. That north-south upload is then used by the central cloud to train much smarter global machine learning models. All right, Section 3, Fog to Fog, Horizontal Coordination. This is all about neighborhood teamwork. Let's step down from the cloud into the middle tier and see how these devices collaborate locally. If edge to cloud is our north-south traffic, fog to fog is our east-west traffic. Instead of taking a long vertical trip up the pyramid, this horizontal communication lets intermediate mini-servers, our fog nodes, chat directly with each other. They share resources, balance workloads, and make decentralized decisions together on the fly, totally bypassing the central cloud. By keeping the compute power geographically closer to the actual physical devices, we're basically swapping out those distant, heavy servers of the cloud for fast, distributed resource sharing right there in the fog. This is huge because it drastically cuts down on internet backbone traffic and absolutely slashes latency. A perfect real-world example of this is a smart city traffic grid. Imagine a massively jammed intersection. You know, the kind that completely ruins your morning commute. The traffic light, acting as a fog node, detects the jam. Instead of phoning a cloud server 3 states away just to ask what to do, it instantly coordinates with the traffic light at the next intersection over, basically saying, "Hey, I'm jammed over here, keep your light green a little longer to clear this out." It's localized teamwork at its absolute finest, drastically speeding up response times. Section 4, M2M, Direct Peer-to-Peer. We call this the instant reflex. Let's zoom all the way down into the very bottom layer of our IoT universe for the absolute most localized model of all.
In this peer-to-peer model, there are no cloud detours. Actually, most of the time, there aren't even fog layers involved. Machines just talk directly to machines. They use highly localized protocols, things like Zigbee, Industrial Ethernet, or BLE, which is Bluetooth Low Energy. And because they bypass the wider network entirely, they don't even need an active internet connection to function.
The entire purpose of M2M communication boils down to reflex-like speed and absolute unshakable reliability. By synchronizing in real time without any internet dependency whatsoever, you completely wipe out the risk of a random network outage causing a local disaster. To really put the speed into perspective, imagine an industrial smart factory. You've got two robotic arms working together on a blazing fast assembly line. Arm A places a delicate microchip on a circuit board, and Arm B has to immediately solder it. Arm A has to signal Arm B the exact millisecond that chip is set. If that signal had to bounce all the way to the cloud and back, total catastrophe. Arm B would strike way too late and literally solder empty air. M2M is what makes those physical reactions completely instantaneous. Finally, Section 5, the ultimate recap. This is your IoT cheat sheet. We have covered a ton of ground today, from data centers up in the sky all the way down to robotic arms on the factory floor. So let's bring all these architectures together. Here is the cheat sheet you need. If you want big data analysis and massive long-term storage, you're going to want that vertical north-south flow of edge to cloud, just like our Tesla sending its telemetry home. If you need regional load balancing without clogging up the whole internet, you want the horizontal east-west coordination of fog to fog, like those smart traffic lights. And for ultra-low latency, instant physical reactions, you absolutely need the localized peer-to-peer connection of M2M, just like our robotic assembly arms. So now that you've got a map of this whole universe, let's look forward for a second. When lightweight messaging protocols like MQTT and CoAP are finally integrated to flawlessly power every single edge device across these three tiers, how radically is our physical world going to transform? When the cloud, the fog, and our machines are all thinking and acting together in perfect, real-time harmony, the possibilities are literally limitless. Keep that on the back of your mind next time you look at the smart devices sitting right in front of you today. Thanks so much for joining me on this explainer, and I'll catch you next time as we keep decoding the tech that's shaping our world.